In this video, we introduce a couple of theories that are going to allow us to calculate rate constants. Right, so let's review what a rate constant is. For a chemical reaction A plus B to give products, okay, if this is a known elementary step, we know that the rate law can be written simply as this: concentration of A, concentration of B. Okay, well, this is the rate constant, and these are just the concentrations of reagents. Now, we have talked at length about what the rate constant is, and we know how to determine it from experiments, right? So the same experiments that allow us to tell whether this is first order and first order also allow us to tell to figure out what the rate constant is. What is more, we actually have also studied what the temperature dependence of the rate constant is, and we said that you can make experiments that measure the reaction rate as a function of temperature, and then you can determine that this is a functional form for how the rate constant depends on temperature. Now, what we'll try to do in this video is introduce a couple of theories that allow you to calculate exactly this rate constant without having to do any experiments. Again, until now, to know the value of the rate constant, you have to do a series of experiments. Again, and what we're trying to do here is avoid any experiments and see if using theories we can come up with values of the rate constants that avoid having to do experiments. Now, having theories that allow you to calculate this is going to be very useful, because with those theories, then we can find deeper meaning to this value of the pre-exponential factor and the activation energy that are parameters in the Arrhenius expression. Right, so there's two main types of theories of chemical reaction rates that we're going to discuss in this video. The first one is collision theory, which is going to be very brief and very simple, and the more important one is going to be transition state theory. Right, so collision theory, we actually have already used it to justify this functional form for the Arrhenius expression. And essentially, at the heart of collision theory, what we have is that in order for this reaction to happen, A and B must collide, and then that collision needs to have the right orientation and also enough energy above the reaction barrier in order to yield products. Okay, so in collision theory, something that is quite important and useful for the future is going to be something that we call a reaction energy diagram. And again, the idea is that you can have a reaction like, for example, O plus H2 to give OH plus H. Okay, and what happens if we actually draw this with detailed bonds is that in the reaction, what happens is that this bond breaks and this bond forms. Right, so this reaction actually happens to be a little bit endothermic. If we plot energy versus reaction coordinate, this is where your reagents will be, and this is where your products will be. Okay, a level endothermic. Okay, so what happens is that as oxygen is approaching the H2 molecule, this bond has to elongate a little bit, okay, because it ends up being broken, and that happens at the time that this bond is not already yet formed, okay, because that only happens in products. Okay, so essentially what happens is that the energy increases a little bit while the reaction is taking place, and the typical energy reaction diagram happens to be like this. Right, so what in collision theory we say is that, well, O and H2, these two reagents, are colliding, but not all of those collisions have enough energy to go above this barrier that we have right here, which is related to the activation energy. Okay, but what we know is that the fraction of collisions that have enough energy above that barrier is actually this factor. It's related to this quantity right here. Okay, so collision theory has a nice connection with Arrhenius theory in that the functional form is the same. The other thing that collision theory does for you is it allows you to calculate this pre-exponential factor in a way that we are not going to see. Okay, and this essentially finishes our discussion with collision theory. Again, it's a nice theory. We're not going to see it in detail. The most important thing about collision theory is that, again, it introduces the concept of the energy diagram, which is quite important, and it also justifies this exponential dependence of the rate constant on the activation energy and the temperature. All right. Now, the theory that really is the most successful theory to calculate rate constants is what we call transition state theory. Okay, so we can write it here. This is where we're going to focus all of our attention: transition state theory. And the focus of transition state theory is going to be right at this point. Okay, that point is the point of maximum energy along the minimum energy reaction path connecting reagents and products. Okay, so we will plot here to use the same example: O plus H2 and OH plus H. In this point right here, that's where we have the transition state, or it's also called an activated complex. Okay, so we can try to draw a little bit how this transition state would be for this reaction. Okay, and we're going to use here geometric parameters. Okay, so the bond in H2 is about 0.7 angstrom. It's a very short bond. The bond in OH is about 1.0 angstroms. Okay, so we can envision that as you go from reagents to products, you reach a transition state in which you don't have either reagents or products. Okay, so typical or reasonable geometric parameters would be a bond that is being formed that is a little longer than the bond that you actually have in product when the bond is fully formed. So we can maybe call this about 1.3 angstrom. All right, and then you have an HH bond, which is not fully broken, but it's a little longer than it is in reagents. So maybe this bond might be of a value of 1.1 angstrom. All right, so again, this is what we call the transition state. And again, the definition is the point of maximum energy along the minimum energy reaction path. Okay, and again, the theory is based on this particular point. All right, so what does the theory say? Well, the theory says that in order for you to go from reagents to products, what has to happen is that you have to go through this transition state, okay, which we're going to call TS, and you usually will see it denoted with this symbol, which is a double dagger. All right. Now, this transition state is not a stable species. Okay, it's a fleeting species, something that lasts for a very, very short period of time. It's either always in the process of breaking or always in the process of being formed. Okay, but again, you cannot isolate it, you cannot put it in a bottle. We will see that under certain circumstances, you may be able to see it using really fast spectroscopic techniques. Okay, and here's the key of transition state theory. Even though this species is actually not stable, okay, the theory consists on assuming that there's an equilibrium between reagents and that transition state. Okay, so essentially what you have is this. And again, this is a little shocking because we expect the equilibrium to be formed between two species that are stable, right? And then they can interconvert between one and the other. But again, now you have an equilibrium between reagents which are stable and a transition state which is not very stable, or not stable at all. It's a fleeting species. Yet, transition state theory, even though it has that approximation, which is a little shocking, okay, it actually works really well, as we're going to see in just a little bit. All right, so then the question is, how can we calculate the rate constant using this concept of transition state theory? All right, the first thing that we can then do is try to write what the rate law for this process would be. Notice that the overall reaction is still A plus B to give products, so we can always write the rate as the rate constant, concentration of A, concentration of B. Okay, and again, our goal is to calculate what this rate constant is with transition state theory. All right, so we can also say the following. Look, you're going to be able to form products, okay, or the rate at which you form products is going to be proportional to the concentration of transition states that you have, and then the frequency, or how frequently these transition states turn into products. Okay, or essentially you can say, well, that the rate for product formation is simply going to be the rate constant of this process times the concentration of that transition state species. Right, so that rate constant and concentration of transition state species, okay, this receives the Greek letter nu multiplied by the concentration of the transition state. And again, that is simply just the rate of product formation starting from the transition state. Now the question is, well, notice that this is an intermediate, and that's something that we don't like in the rate law. So the question is, how are we going to solve that? Here's where the equilibrium approximation is very useful. Notice that if there's an equilibrium in this step right here, we can write that the equilibrium constant for that step is equal to the concentration of transition state species over the concentration of reagents. And this allows us, gives us a handle to put the concentration of transition state species as a function of the concentration of reagents. Notice that this transition state species is just going to be equal to the equilibrium constant times the concentration of A times the concentration of B. Okay, so now we can take this concentration and replace it here in the rate law, and we will find that this is equal to nu, again, which is just how frequently this transition state falls into products. Okay, multiplied times the equilibrium constant, concentration of A, times concentration of B. Okay. Now, if we examine this expression for the rate law, which is the general one, just taking into consideration reagents, and then what we have obtained from transition state theory, we see that they are essentially the same expressions if the rate constant, which is what we want to calculate, is equal to this nu, frequency of the composition of the transition state into products, times this equilibrium constant between reagents and the transition state. Okay, so that is going to be the key of transition state theory. The idea here is that by comparison of these two expressions, then the rate constant K, which is what we want to calculate, is going to be equal to this nu multiplied by the equilibrium constant between reagents and the transition state. Alright, it turns out that this frequency of the composition of the transition state into products has already been calculated by some people, okay, and we actually know that this number is constant. It's not constant, it depends on temperature, okay, but it has this value always, where K sub B is simply something that we call Boltzmann constant, H is something that we call Planck's constant, and T is the temperature. Okay, so these values, which we will become very familiar with in future chapters, that is 1.38 10 to the minus 23 joules per Kelvin. This H, which is Planck's constant, is 6.626 10 to the minus 34 joules second. And then if the temperature is 300 Kelvin, which is about room temperature, this factor happens to be 6.26 10 to the 12 per second. Alright, so let's examine a little bit what this frequency of the composition is. You notice that this is about 6 trillion per second. Okay, so what that means is that once you have a transition state, this transition state attempts to decompose into products about 6 trillion times per second. Okay, so the motions of this transition state in which it might towards progress, they're extremely fast. Again, they take place about 6 trillion times per second. And this gives you an idea for how fast chemical reactions are and how short-lived this transition state is. Okay? Well, this nu is just one of the pieces of the rate constant. The other piece is this equilibrium constant, which turns out that is quite complicated to calculate, and we're not going to see it in this course. But suffice it to say that today we actually, using computers, so no experiments involved, using geometries of reagents, products, transition state, the energies, we can actually calculate what this equilibrium constant is, and then we can compute with very high accuracy what the values of rate constants of chemical reactions are. Okay, so again, this video in summary is simply just an introduction to what a theory of a chemical reaction rate is, what the goal is, which would be to attempt calculation of the rate constant, and it also serves as an introduction to the most successful theory that we can use in this course, which is transition state theory, with an explanation of what a transition state is and how we formulate the theory. Now in the next video we're actually going to see this same theory, transition state theory, but we're going to try to analyze it from a thermodynamic formulation, which is going to be based on this equilibrium that we have here between reagents and the transition state.